Let's try another example. Let's try two more before I get into the new stuff. Let's try example 2 for our warm-up. Let's see here. Shrink that. So go ahead and draw this parallelogram here. Would be number 2. So this is a parallelogram. Going to draw that one, please. Parallelogram. Copy that one down. All right. Out of the 4 theorems that I threw at you on Thursday in your note packet, from theorem 6.2 to 6.5, which one of those theorems has to do with the sides of a parallelogram? 6.2, huh? Ms. Castro, what does it say about the sides of a parallelogram? Can you read it to me? Yes. What does it say? Opposite sides are congruent. Straightforward. That means this side right here is congruent, the same size of that side. Right? And the same one with the x's. These two sides are congruent. Right here, that's congruent to that one. That's pretty straightforward. We can solve for the variables now, knowing that the two sides are congruent. It's a lot more easier, a lot more straightforward than example 1. So, using theorem 6.2, the reasoning, the logic of 6.2, I'm going to say, you know what, 3y minus 7, that's going to be the same size as 2y plus 4. It's a parallelogram. Theorem 6.2 tells me so. Right, Catalina? So we have an equation with y on both sides. How can I get y on one side, though, Desmond? What do you think I can do to both sides, Desmond? How can I get y on one side? From both sides? Yeah.
Add 2y.
Subtract 2y.
Right, subtract 2y from both sides, or subtract 3y from both sides. Either way, you still get the y on one side. So let's do it this way. This will avoid negatives, make us less prone to mistakes. So I got 1y minus 7 is, yeah, that. And then to get y by itself, what should I do to both sides? Buckley, what do you think? What do you think, Buckley? What should I do to get y by itself here? What do you think? No problem. Ellen's going to come to the rescue. Hit it, Ellen. Nice. So y is 11. Half the mission's over. Let's solve for x now. X equals what? So what's the equation you set up now? Give it to me. I like it. Very nice. So now, y solve for, so the equation we use for x will be this side is equal to that side based on theorem 6.2 that Castro just read about 3 minutes ago. So look at 5x now is equal to 3x plus 18. Cool. Let's subtract 3x from both sides, or subtract 5x from both sides, don't matter. Here we go. Oops. Subtract 3x. So subtract 3x from both sides. And we get 2x is 18, divided by 2, x is 9. Done. Gotta orient my board here. All right, last one. Let me go ahead and grab this one and put it down here. Last one for warm-up. All right, number 3. This will be example 3. Here's a parallelogram. Want to draw this? I'll give you a minute to draw it. So on number 3, we're trying to find out what theorem deals with diagonals. 6.5 deals with diagonals. Exactly. So 6.5, theorem 6.5 says something very specific about diagonals. And it uses the word bisect. Thursday I talked about what bisect means. Anybody remember what bisect means? Cut it half, chop it half. Theorem 6.5 says, look, this diagonal right here, it chops in half, it bisects the other diagonal. In other words, this diagonal now is chopped right in half. So I have this little segment and this little segment being congruent. And then vice versa. This diagonal chops this diagonal in half. They chop each other in half. It's a mutual chopping in half, so to speak. So I know that this segment and this segment are not congruent. This segment and this segment are not congruent, so that's pretty straightforward. You can see the obvious equation that will result from that logic. We'll be able to solve for x and y. So 7y minus 2, 7y minus 2 will be, 7y minus 2, right, equals 5y plus 4. Again, the logic we're using is the logic provided by theorem 6.5. The diagonals bisect each other. They chop each other in half. So you have two resulting segments congruent. So the rest is algebra like we've been doing. Let's subtract 5y from both sides. So at 2y, 4. At 2, y is 6, divided by 2, y is 3. Cool. Let's solve for x now. It's the other diagonal, right? So x, so that means this segment and this segment are congruent because this diagonal chopped it in half. So I have 3x plus 2 is 23. Cool. Let's get x alone. Let's isolate it. 3x then is 21. X is 7. Beautiful. So we pretty much, with these 3 examples, we covered all 4 theorems. We used all 4 theorems here that I threw at you on Thursday. All right. Questions? Sure. I'll put that up.